Hello everyone, I'm back with yet another very popular interview problem. So today we are going to discuss DFS in a graph, and this is probably the most basic concept when it comes to graph algorithms. And generally in interviews, this algorithm won't be asked as such, it would be hidden inside another problem. So there are a lot of problems which are applications of DFS. So when you are given that problem, you will have to figure out deep down inside we are using DFS to actually solve the problem. So this is an underlying concept that is a building block to several other problems. So it is very necessary to know this, because if you are learning graph, this is probably the first thing you should know. So let's begin. So before I go on to this problem, I'd like to quickly take a moment to discuss what the representations of a graph in our problem would be, and how we can implement DFS and what exactly DFS is. So you can see that there are two different representations of graph that we generally use. One is adjacency matrix and adjacency list. So let's take an example of this graph that I put in the box over here. If you want to know more about it, if you have no idea what this is, then take a pause and learn about it a little bit and then come back over here. So just to simplify things, I just took this small graph and I'm going to represent it by using both adjacency list and adjacency matrix. So in case of adjacency matrix, what we do is we create rows and columns which is equal to the number of vertices in the graph. So here we have three vertices, 1, 2 and 3. So 1, 2 and 3 and 1, 2 and 3 rows and columns. And this ijth element would represent whether we have an edge from that ith element, ith vertex to jth vertex. So in case of this graph, we have a edge from 1 to 2. So 1 to 2, this I is 1 and j is 2, there we will have a 1. And if it is 0, then it would mean that there is no edge between those two vertices. And we have a edge from 1 to 3, so we have a 1 over here. Similarly, the opposite is also true. These are undirected graphs. In case of directed graphs, it's a slightly different story. We'll discuss that in the coming videos. And you will also notice that in case of adjacency matrix, in these representations, it is symmetrical with respect to the main diagonal. And that is meant to be. You will already know why it is if you look at it. And in case of adjacency list representation, it is more space efficient. But adjacency matrix provide another advantage, that you can you can see if there is an edge between two vertices in order one time, but it is not possible in case of an adjacency list. So in case of an adjacency list, what you simply do is first provide the vertex and give all the elements which are adjacent to it in that list. So all the vertices adjacent to 1 is 2 and 3, so they are both given in that list. For 2, we just have one element adjacent to it, that is 1, and 3 we just have 1, which is 1 itself. So those are the two representations, and in this problem we are actually going to use adjacency list representation. And let's take an example of a graph and discuss what DFS is. If you know what DFS already is, then you can skip forward, else you can just see. So DFS is generally called at a certain vertex that you can decide, can be an arbitrary vertex or it is something that is already given to you. So let's start the DFS of this graph from 0. So we will actually be keeping an additional data structure to see if the vertex that we are currently exploring is visited or not. If it is already visited, then there is no point in going there and exploring it again. So we will probably be using a visited map or a vector to actually check if that vertex is visited or not. So initially we start exploring from 0 and we mark this vertex as visited. And in this adjacency list of 0, we will have 1, 6 as well as 7. So let's say we start exploring from 1 and we mark 1 visited and check its adjacency list. We have 2 and 3. We go to 2 and explore its adjacency list. There is no other element, so we can return back. We come back over to 1 and then we explore the rest of the elements in the adjacency list of 1, which is 3. Then we go to 4 and in the adjacency list of 4 we have 5. It is explored, and we go to 3 again. There is a call from 5 to 3, but we know that 3 is already visited. Because of that, we just return back. And since we have explored all the vertices over here, all the calls, the recursive function calls, will return back, and it will go back to 0 and see what are the other elements remaining in the adjacency list of 0, which includes 6. After that, it goes to 7, and the whole graph is explored. And we'll have a pattern actually. So since we are exploring from the left hand side, it will be like 0, 1, 2, then 3, then we go to 4, 5, then we go to 6, and then 7. So we'll have elements in the ascending order here. So that's the basic idea of DFS, and let's see how we can actually implement it. So I'm going to clear this off, and let's start implementing it. So we are given 2 inputs actually. One is the number of vertices, and the other one is the adjacency list that we would need. So we are supposed to return an answer in a vector. So I'm going to make that global, and this is where we are going to store our answers. So the reason why I'm making it global is that we are going to write another function for DFS, and in that function we'll be using this vector. That's why I made it global, or you can pass it by reference, whatever you are convenient with. And so we'll be needing one more data structure, which I said I'm gonna use an unordered map. If you are not familiar with this, then you can quickly take a moment and rediscover it. Go to Geeks of Geeks website and figure out what this is. Right. I'm going to make first data type. The key would be int and the value would be bool. So this is what I use to see if an element is already present or not. So I'm going to name it VIS to see if a node is already visited, and I'm going to make a DFS call. I'm going to write another function DFS for that, and in that function I'm going to pass the first vertex where we are going to start the search. So in the question it is mentioned that it should start from the 0th vertex from left to right according to the graph. So I'm going to start with 0, the first vertex which I'm going to explore. I'm going to pass the adjacency list, and I'm also going to pass the visited map. And finally I'll return the answer. So now let's implement the DFS function. So I'm going to make it void because it won't return anything, and I will have to give the first parameter as the vertex. I'm going to give the letter V to indicate that vertex, the current vertex that we are exploring. Then there is the adjacency list. So it has the data type of int and bool. So first thing we have to do when we call a DFS is to mark the current vertex that we are exploring as visited. So let's mark that first. So VIS of that element, we make it 1. So 1 means true. So instead of true, you can simply write 1. And once we are at a certain vertex, then we can push it back into an answer, because as we are exploring, we need to populate our answer vector so that we can return it in that specific order. So let's put that element into our answer vector. Push back. So push back V, and once we have done that, then we can do a for loop. So let's put the size of the adjacency list of the current element that we are exploring in a variable n. So that would be adj of the current element. So that will be V, and its size, I'm going to put that size in n, and I'm going to put a for loop to actually explore through the adjacency list of that element. and we check if it is visited. If that element is already visited, then only we make a DFS call over there. VIS of V. So we'll have to check the specific element. So we are exploring through the adjacency list of that element, and in that element we'll have to check for each element in the adjacency list whether we have already visited it or not. So only if it is not visited, then we are going to explore it. So not equal to VIS of a adjacency list of V and I. So we are going to explore through the adjacency list of each element, and for each element in that list we see if it is already visited, and if it is not visited, then we make a DFS call to that. So DFS of that element, which is ADJ of V comma I, and we put the other elements also, that is ADJ and the map. So that is pretty much it. Actually pushing it back, we are marking it right, and we are exploring. So that is the whole code. Actually, let's see if that works. So we got the output for the sample test case. Let's see if it works. So we'll have to pass the map by reference, because if we pass it by value, then every time we'll create a new map. But we don't need that. We'll need a common map for all of them. So we'll pass the map by reference, or we can make it global as well. Both of them will serve the same purpose. And there we go, problem solved. And that is pretty much it for this problem. Very simple concept, but it is the base of over 50% of the graph problems, I believe. So it is very important to know that, and I'll see you guys in the next video. Goodbye.